Let's take a look at the next example on the implicit differentiation. Now in this example, you are required to find the value of dy dx and d2y dx square at this specific point on the curve of this. Okay, so you know you're going to use implicit differentiation. Why? Because if you look at this expression here, you cannot easily make x the subject or y the subject. So what do? We do implicit differentiation like that, just as this line. Again, it is about term by term. So if we differentiate this x, or rather y cubed, you will get 3y square, and then you have to use product rule on this. You use product rule, correct, on this, and differentiate 1, you get 0. So very quickly, let us use product rule on 2xy. You will get this, and then differentiate y cubed, you get 3y square dy dx. Right, we slightly simplify it. I don't think there's a lot of simplification, but we slightly remove the bracket, we get this. Now, quite easily, if you want to find dy dx from here, we can now substitute x equals to 1, y equals to 1, right into this, right into this. Not a problem, we can dy dx. But let's hold our horses first. We don't substitute first, later we substitute, not a problem. But ultimately, we still want to find the 2y dx squared. Now, most people like to make dy dx the subject first, then differentiate. My suggestion is no. There is no need to make dy dx the subject first before another differentiation. We can do another layer of differentiation term by term from here, and I can guarantee you it's a lot easier. So, alright, we're going to do term by term differentiation on here, 3y squared dy dx. Let me use a different colored ink, maybe it's better. Alright, now this one, this term here is from differentiating this. Let me be very clear. Use product rule. Again, I want to emphasize product rule. Alright, and then these terms here, these two terms here, are from differentiating this using product rule again. Okay, you can take a look. Okay, keep one, differentiate the other. Of course, you differentiate minus 2y, you get minus 2 dy dx. So this is how it works. It may look complicated. You take a quick look at it. I don't think it's terribly difficult. But I want to emphasize at this point now, here you have a dy dx and you have a dy dx. Dy dx times dy dx, you actually get a dy dx whole thing square. So dy dx whole thing square actually is not the 2y dx square. Okay, I want to emphasize this. That is why in the next line, yes, you get this dy dx whole thing square here. Alright? Yes? Then this one you simplify, you simplify, and we are done. So now we are not totally done. Alright? We want to find the value of dy dx at x equals to 1, y equals to 1. So when I'm going to continue. When x equals to 1, y equals to 1, I'm going to substitute it into here. Alright? Therefore you get 3 dy dx minus 2 dy dx minus 2 equals to 0. Alright, quite obvious. Dy dx must be equals to 2. So we found this answer. Now, same thing. Alright, I'm going to substitute it into this one. Yes, I'm going to substitute into this one. So, and when dy dx, or rather when y equals x equals 1, y equals 1, dy dx is 2. So I substitute these three values, 1, 1, 2 into here. So I get 3 d2y dx squared plus 6 2 square minus 2 d2y dx square minus 4 times 2. You work out the arithmetic, d2y dx square equals to, work, I'm quite sure it's not difficult, you get negative 16. So there you got your two answers, 2 and negative 16. I want to emphasize this again, that over here you must use product rule properly. Alright, and here your dy dx square is not d2y dx square. So don't use them interchangeably, because this term and this term are very different. Alright, that's that. Thank you.